So in this video we're going to go over how to draw a Lewis dot structure that obeys the octet rule. So I'm following these steps over here off to the side, and depending on what your structure ends up working out to be, you may end up using all 6 steps or you may not. So we're going to do this first for an ion, and the ion we're going to do is the phosphorus tetrachloride with a positive charge ion. So the first step is to draw the skeletal structure, or just the general layout of where these atoms are going to be in relationship to each other. So generally you're going to put the least electronegative atom in the center, so between phosphorus and chlorine, that's chlorine, or sorry, phosphorus is going to be in the center. So I'm going to draw a phosphorus in the center, and then I'm going to draw the 4 chlorines just around it, just one on each side for simplicity. And I'm just going to draw a bond connecting them. So there is my skeletal structure. The second step is to count the total number of valence electrons that you have. So phosphorus in group 5 has 5 valence electrons. Chlorine in group 7 has 7 valence electrons, but we have 4 of them, so we're going to take this 7 and multiply it by 4. And then we also have this positive charge. So remember, if you have a positive charge, that means you have lost an electron. So I'm going to subtract an electron here for that positive charge. So 5 plus 7 times 4 minus 1 adds up to 32 electrons. And remember, we're only worrying about the valence electrons because those are the only ones involved in bonding. So these 32 electrons are kind of like our bank. How much money is in our bank, and we have to balance our checkbook at this point. You spend electrons whenever you put a bond on your structure or a lone pair of electrons. So just drawing our skeletal structure, we've already spent electrons for these bonds. So step 3 is to subtract 2 electrons for each bond in the skeletal structure. So I have 4 bonds, so I'm going to go ahead and subtract out 8 electrons to account for those bonds I've already drawn. Balancing the checkbook, I'm left with 24 electrons. Step 4, we're going to complete the octets of the terminal, meaning those on the outside, atoms by adding pairs. So every atom is going to want 8 electrons, except for hydrogen just wants 2, because they want to look like a noble gas. So chlorine currently has access to 2 in this bond, so it needs 6 more to get its octet. So we're going to move them in pairs. So I'm going to put 3 pairs, so now I have 2, 4, 6, 8 electrons around this chlorine. I'm going to do the same thing to the other 3 chlorines. So each chlorine got 6 electrons, so 6 times 4 is 24, and I have just spent 24 electrons. So when I go to balance my checkbook, I have to subtract the 24 electrons that I just spent, and now I have no more electrons left. So step 5, if any electrons remain added in the central atom, we're going to skip that because we don't have any electrons left. Step 6 says if the central atom does not have an octet, we're going to move an electron pair from a terminal atom to make a double bond. So let's see if our central atom has an octet. So this is phosphorus. It has access to 2 electrons in every bond. So 2, 4, 6, 8, it's already got an octet, so we can skip that last step. The only thing we have left to do is, because we are a polyatomic ion, we have a charge, we need to put this whole thing in brackets and put that charge on the outside. So that is how to draw the Lewis structure for a simple polyatomic ion that obeys the octet rule. In this next problem, again, we have a polyatomic ion, and again, we're going to obey the octet rule, but we're going to see something's going to end up being a little bit different with this one. So we're going to follow the same 6 steps. So step 1 is to draw that skeletal structure. Again, you're going to put the least electronegative element in the center, and in this case, between these 3, carbon is the least electronegative. So we're going to put carbon in the center and just put the nitrogen and oxygen out to the sides. Step 2, we're going to count the total number of valence electrons. So I have down here, oxygen in group 6 has 6 valence electrons, carbon has 4, nitrogen has 5, And now we have a negative charge on our polyatomic ion. So a negative ion means you have gained an electron. So we're going to add an electron here. So 6 plus 4 plus 5 plus 1 adds up to 16 electrons in our bank. So step 3, we're going to start balancing our checkbook. Subtract 2 electrons for each bond. We've already drawn 2 bonds, so we're going to subtract 4 electrons. So we're down to 12. Step 4, complete the octets of the terminal atoms by adding the pairs. So oxygen and nitrogen each want 8. They currently have access to 2, so they're going to need 6 more apiece. Now in this case we had enough electrons to go around for everybody to get 6. If we didn't have enough, then the more electronegative terminal atom, in this case that would be oxygen, would get first dibs on those electrons. So we just spent 12 electrons, so our checkbook is down to 0, which means we can skip number 5. Now step 6 says central atom does not have an octet. Move an electron pair from a terminal atom to make a double bond. Carbon currently has access to 4, and it's going to want 8. So that means we need to start moving electrons from a terminal atom. So if I move this pair of electrons here, now that becomes a double bond. Now carbon still does not have an octet. So at this point we have multiple possibilities. We could move another pair from nitrogen, we could move a pair from oxygen, or we could have moved 2 pairs from oxygen instead of from nitrogen. So here are the 3 possibilities we would end up with. Make sure when you move that this pair goes away because we're moving it, we're not doubling it. So we could end up with carbon in the center, a triple bond to nitrogen, which means that 2 pairs had been moved, so nitrogen's just left with 1 pair to itself, and we didn't touch oxygen. Or we could have moved double bonds on both sides. So nitrogen would still have 2 pairs, and oxygen would still have 2 pairs. Or we could have moved triple bond from oxygen and left nitrogen alone. Now, all 3 of these structures, you can put brackets around them and put the negative charge on the outside, all 3 of these structures do obey the octet rule. They all have 8 electrons around each atom. They all have a total of the 16 valence electrons we started with. So we didn't break any rules making these, so all of these are technically possible. The way to figure out which one is the most likely structure lies with the idea of formal charge. So let's assign formal charges here. I'm going to change colors so we can assign formal charges. So formal charges, again, are the number of valence electrons an element started with, so these numbers here, minus how many electrons are associated with that atom, meaning if it were to break away, how many would it take with it. So let's look at this first structure here. So let's look at oxygen first. Oxygen is in the group 6, so it starts with 6 valence electrons. This oxygen atom, any lone pairs belong to it, so that's 2, 4, 6. And for the bonding, it technically only owns 1 of them. So it's only got 1 there. So 6 plus 1 electron from the bond gives us 7. So 6 minus 7 means that oxygen has a formal charge of -1. Oxygen starts with 4. 4 electrons minus, for each bond it only gets to keep 1 if it were to be broken out. So 1, 2, 3, 4. So it has a formal charge of 0. Carbon almost always has a formal charge of 0 in most structures. And then the nitrogen started with 5 minus, we've got 2 electrons in the lone pair that belong to it, plus it gets to keep 1 for each bond, so 1, 2, 3, 4, 5. So a formal charge of 0. Now the sum of the formal charges has to add up to the charge on the overall molecule, which this is a polyatomic with a -1 charge, so our formal charges are -1 on the oxygen, 0 on the carbon, and 0 on the nitrogen. That adds up to -1, so we're good. If we do the same thing down here, now this oxygen, again starting with 6, but it only has access to 1, 2, 3, 4, 5, 6 associated electrons. So now it would have a formal charge of 6 minus 6, or 0. Carbon, again, still has access to, or has 4 associated, so it's still 0. Now this nitrogen has associated 1, 2, 3, 4, 5, 6. So 5 valence electrons minus 6 associated, it now has the -1 charge. So far at this moment it looks like these two structures are equal and that both of them have the -1 charge that adds up here. Now let's look at this last structure here. Now this oxygen here has associated 1, 2, 3, 4, 5 electrons. So 6 minus 5 gives it a +1 formal charge. This carbon still has 4 associated, so 4 minus 4 still has a 0 formal charge. Now this nitrogen has associated 1, 2, 3, 4, 5, 6, 7 associated electrons. So 5 minus 7 gives it a -2 formal charge. Now this still adds up to the -1 on the molecule, so these are still valid formal charges. But the best, most stable structure is always going to minimize formal charges, have them as small as possible or in as few formal charges as possible, which means this structure is going to be the worst because it has the most formal charges and they're bigger numbers, so -2 instead of just a -1. So that's definitely not our best structure. These two are going to look the same at first, except for the rules of electronegativity. Electronegativity tells us which elements are going to pull electrons towards themselves more strongly. So in this structure, oxygen has the negative charge, or the extra electron. In this structure, nitrogen does. Between oxygen and nitrogen, oxygen is more electronegative. So it's stronger to pulling electrons towards itself, meaning it can handle a negative charge better than nitrogen, which means that this structure up here is going to be our best structure according to formal charges. So that is how to draw a Lewis structure of a polyatomic ion, and using double bonds to make sure that you satisfy the octet of the central atom, and then using formal charges to determine between multiple possible structures which one is going to be our best structure.